Today we are going to see steady state of a stochastic matrix. A stochastic matrix that is a square matrix with all entries of greater than or equal to 0 and sum of row entries is equal to 1. Furthermore, state y is obtained from x. So according to y transpose equal to x transpose into A. Another name of stochastic matrix is a Markov matrix. A stochastic process satisfies the future behavior of a process depends only on the present state but not on the past. The process is Markov process. A discrete parameter Markov process is called a Markov chain. Otherwise, a sequence or a chain satisfies the Markov property, then we can say it's a Markov chain. The most important fact about the Markov chain, eigenvalue of the stochastic matrix is lambda is equal to 1 is an eigenvalue. Point 2, the eigenvector associated with lambda equal to 1 can be chosen to be strictly positive. And the third point, all other eigenvalues magnitude is less than 1. Suppose u0 is a positive vector whose components add to 1 . This is true if and only if equal to 1. If A is a positive Markov matrix. The product of u1 equal to a into u0 will also be a positive vector with the component adding to 1. This because of A is a matrix, all of whose rows add to 1. By induction, we can write a k u0, a power is a positive vector. The steady state is given by the eigenvector associated with lambda equal to 1. The reason for this that we can write u0 as a linear combination of eigenvectors. So u0 is equal to c1 vector 1, c2 vector 2 plus etc. plus cn vn vector n. So a into u0, so c1 a v1 plus c2 a v2 plus etc. plus cn a vn. In general, a power k u0 that is equal to c1. Now a power k, we can write av is equal to ax equal to lambda x, then lambda 1 power k v1 plus c2 lambda 2 power k v2 plus etc. plus cn lambda power k vn. So ax equal to vx lambda x. But lambda equal to 1 is eigenvalue and magnitude of other eigenvalues are less than 1 for I is greater than 1. So that means lambda equal to 1 c1 into 1 power k v1 plus c2 into magnitude of lambda I power k v2 and etc. So this one is equal to c1 v1. This lambda magnitude of lambda is less than 1 as k tends to infinity. The vector will be approach c1 and v1 only, which will be the steady state solution. Yes, lambda I is less than 1, so this one belongs to 0, so only we get c1 and v1. So c1 v1, which will be the steady state solution. Note that assumption c1 not equal to 0, corresponding stochastic matrix. Example, assume in a year of 2020, in a city people saw use for traveling inside the city. Cycle 30%, bike 20%, and car 50%. Assuming that the transition probability for 1 year interval, we can take cycle, bike, and car. Cycle, bike, and car. Is 0.8, 0.1, 0.1, 0.1, 0.7, 0.2, 0, 0.1, 0.9. That means the 1 year transition cycle to cycle 0.8 probability value, cycle to bike 0.1, cycle to car 0.1. Then the transition move bike to cycle 0.1, probability of bike to bike 0.7, probability of bike to car 0.2. Then car to cycle 0, car to bike 0.1, car to car 0.9. If all the entries are greater than or equal to 0 and row sum is equal to 1, 0.8 plus 0.1 plus 0.1, that value is 1, and is a square matrix, so it is stochastic matrix, so Markov chain matrix. The sum of 100% should be rewrite in the matrix from the given values. Initial value, let us assume the initial value x transpose equal to 30% cycle, 20% bike, and 50% car. So do we know that this y transpose equal to x transpose into A? So we can write 30, 20, 50 into 0.8, 0.1, 0.1, 0.1, 0.7, 0.2, 0, 0.1, 0.9. Now we are going to find the expected value of another 1 year. So just multiply row into column wise. So 30, 20, 50. In transpose, we can write 26, 22, 52. Y transpose. That means after 1 year, 26% people are used cycle, 22% they used bike, and remaining 52% people used car for traveling. But this one is one step transition probability. The limit is reached if the states remaining unchanged. That means A transpose X equal to X. This means that A transpose should have the eigenvalue 1, but A transpose have the same eigenvalue of A. With eigenvector V transpose 1, 1, 1 transpose. Because the row sum of A is equal to 1 and the non-trivial solution of X because the row sum of A equal 1. So A into B, that is equal to 0 0.8, 0 0.1, 0 0.1, 0 0.1, 0 0.7, 0 0.2, 0, 0 0.1, 0 0.9 into the vector 1, 1, 1. Definitely we get the value 1, 1, 1 as climbed. The non-trivial solution X not equal to 0, which is an eigenvalue, lambda equal to 1, is an eigenvector of A transpose corresponding lambda equal to 1. So now A transpose minus I into X equal to 0. So the rows are dependent. So it's a single matrix. So determinant of A transpose minus I equal to 0. So we get lambda equal to 1. So A transpose and A have the same eigenvalue. Here we need to find out the eigenvectors corresponding A transpose. So we can write 0.2 x1 plus 0.1 x2 equal to 0. 0.1 minus 0.3 plus 0.1 x3 equal to 0. 0.1 x1 plus 0.2 x2 minus 0.1 x3 equal to 0. So solve this equation. We get 0.125, 0.25, 0.625. The solution with the sum of the components equal to 100%, that is X transpose equal to 12.5, 25, 62.5. Assuming that the probabilities remains the same as time progress. That means the people traveling inside the city. In future, according to the present state, 12.5 percentage cycle, 25 percentage bike, and 62.5 percentage people use car.